Hey everyone, my name is Taylor Sparks. I'm the editor-in-chief of Integrating Materials and Manufacturing Innovation. I've got a brand new paper to talk about, and it's all about getting data out of the PDF and into machine learning ready tabular spreadsheets. Right? This work comes to us from authors Immanuel and Mahata at Merrimack College. Now, this idea that we're going to pull data out of the literature, what they're working on specifically is getting things like yield strength, tensile strength, elongation from additive manufacturing data. We would love to do that, but it's a challenge. In the past, we relied on things like regular expressions or regex, right? Basically, these are like a rules-based way of parsing data out, and it was not very good, right? It struggled with understanding context. It didn't adapt to all the different data formats. It really struggled, definitely with tables and figures as well. So there's been this push in recent years to move towards large language models to extract it. In fact, one comes from my own group, published right here in IMMI. We use Gemini Pro to do essentially structured prompts to make this hand labeling process not quite so awful, to teach a machine learning algorithm how to pull data out of literature. These authors are going to try and do something similar, but with an advancement, a modification. They're going to combine the large language models that have been used in literature, things like Gemini 2.5 Flash. They're going to combine it with object-oriented software design to come up with a system that can do not only data extraction, but also querying, right? So it says here the software incorporates a question and answer module that lets users interact with the data directly to get deeper insights. Let's check it out. So essentially they're building out two things. The first is their Alloy data extractor class. And this is essentially the tool that pulls the data out of the literature. So they hype it up. They tell it you're a lean, mean, materials data extracting machine. Here's the prompt telling it essentially how this is going to take place. And then they can turn it loose. Like here they show how via the API call, they can take papers and extract out JSON extracted data text and put it together in some sort of spreadsheet like a CSV. Now, the second thing that they built is this question and answer module for knowledge retrieval, right? And when you start to look at how they built this, you realize it's essentially a RAG system, right? For all the potential information, they go ahead of generating vector embeddings for each string. They use Gemini's embedding model. Once you have those, you put together a database. In RAG world, we call this the vector database, right? They have the similarity search that takes your user's prompt and figures out which chunk of text in this data that you've extracted is the closest match to it. And then it returns n number of those embeddings, right? So that they have content to pull from. And it says right here, these relevant records, along with the entire process data set converted to a string, are then provided as the context for the model. And then it has a carefully crafted guidelines. It basically tells it to answer the question as if it was a material scientist who's going to refer exclusively to this data table. Pretty cool. So in any time when we're building one of these models, we're interested in performance. So what is the score for accuracy, precision, recall, and F1 score? It looks pretty dang good. Check this out. They're scoring it with and without complex graphs. They actually benchmark it against times based off the number of PDFs that they gave it, right? So they had two scenarios. They had one where they had 18 PDFs, 8 megabytes each, took about 5 minutes to extract the data. But check out this one. 286 PDFs took about 59 minutes. So these are not crazy times to get that data extraction. Then when it comes to the question and answer, here's some examples. Which alloys have a larger titanium concentration? It's able to pull a couple of those out. Does the alloy FeCu have high elongation? And it says, I'm sorry, I cannot say definitively whether it does. The dataset only contains pure carbon, right? It doesn't have this iron alloy, right? So it does a pretty good job of providing correct answers, demurring when it doesn't have the context to provide the answer. This is pretty slick. They do a couple of other things. They explore how the embedding space works, and they're particularly interested in seeing if it's preserving physically meaningful properties. So they actually do the embeddings, and then they take the distance in the embeddings, and they compare that cosine similarity with the properties to show that there's the expected trend here. Ultimately, they go about creating a test data set where they actually can train on something and then try it out and see what sort of performance they get. And it's not bad, right? R squared's in the 0.7. The root mean square error on these things are, depending on the property you're looking at, for example, yield strength, it's something like 80 megapascals. Not too bad. So in summary, what they've created here is a modular object-oriented framework for automated data extraction and a question answering tool, and they've deployed it on alloy-focused literature. And like everything in our journal, we focus on fair data. So sure enough, you can see the code that was actually developed here on their GitHub page and try it out yourself. So check it out in the latest issue of IMMI.